better. All right, so let me see. If you look at the relative curve, all right, so you see how this one looks like, right?
Yeah.
So we could easily try to arrange it to look like what we have here. All right, so what we are going to do is we want to create a secondary axis so that we have two separate axes for water saturation and for oil saturation. Because if I look at what I have here, especially this one up, you realize that you have water saturation and then you have oil saturation. They're easy different.
Yes.
All right, so if I come here, I'll come, let me see design. If I click the curve, I go to design. All right. So I look at quick layout. If I choose this last one here, down here, it gives me the name of this curve so that when I look at this, I already know how this is relative permeability of oil, and then this is the one of water, right? So that I know each of them. All right, so I want to create a secondary curve for relative permeability of oil. I will click on this, then I'll right click, I take format data series. When I click on format data series, I see this will appear here, and I click on secondary. Once I click on secondary, you see that it has created a secondary axis, right?
Yes.
So we have to know that this secondary axis is for oil saturation, oil permeability, relative permeability of oil, because that was the curve that I clicked. If I come now to this art chart, if I take axis, what I will be seeing now are four axes. I have primary axis, two primary axes, and two secondary axes. But they have not toggled this horizontal, so I can toggle the horizontal on, and I see that another horizontal now appears up there.
Yes.
Okay, so what I will do now is, once I click on any number on any axis, it highlights that particular axis. Once it highlights that particular axis, I click on a number again, and I take format axis. All right, I want to arrange this scale. I want to arrange it, let it be from 0 to 1. So this is a minimum, and that's a maximum. So I'll put a maximum at 1. I'll put a maximum at 1. Yes, arrange it. I will come down here also. I click on the number. Oh, it's okay. Since I click on the first time, it just appears here. I will change this one to 1 again. All right, this axis, I'll still do the same because relative permeability, the maximum also is 1. So I will do the same thing. I will change this to 1. Then I'll take this axis also. Remember, this axis ending just at 0.25. I'll take it also to 1, like that. Okay. So if water is increasing in one direction, I expect that oil saturation should also increase in the opposite direction. So if this is my primary axis, which is for water saturation and relative permeability of water, this secondary axis is for oil saturation and then relative permeability of oil. So I want the relative permeability of oil to increase in the opposite direction. Oil here and I have 100% water here. So as water is gradually reducing, oil is gradually increasing. So I will take this, then once I click on it, this box of format axis will appear. If it doesn't appear, I will still right click and take format axis. But since it's already there, there's no problem. I can see values in reverse orders. I can see values in reverse order. So I will click the value in reverse order. The values have gone in reverse order, but another problem has been created because this secondary values that was here now is not on this other side. I will click the value. I want to change the direction back of the value. If you want to change the direction of the vertical axis, I will highlight the horizontal axis. I will highlight the horizontal axis. I am still at format axis. Since it is automatic, I will take maximum. Once I take maximum, it changes the direction of the vertical axis. Now, if I want this axis up to come down so that it looks like this, I will now click the vertical axis this time around. I'll click the vertical axis this time around. Then I take maximum also. Oh, all of them have, no, let me take it back. Let me take this one on this side. And then I take automatic. All right, that's right, it comes down. So I now have the two values up. I 0% oil. This is 0% water, 100% oil. I will go to layout and then I will indicate the name. This is axis title. It should appear here. Even the one of, let me see. Even this other one also should appear. All right, so this one now, I will change this one now to relative permeability of, the two of them are, this is relative permeability of oil. So we can just leave it as KRO. Then this one is just relative permeability of water. Relative permeability of water. KRW. This one up here is water saturation, which is okay. Then the minor axis now is the minor axis now is oil saturation. So it gives me SO. So the curve now look more better than the first one. Then this scale, I think this scale has changed. This is still from 0 to 1, but this one is, I will take format axis. Or if I don't take format axis, I take this last one. Oh, it should be one of them. All right. No, not this. Let me see. Format axis. All right. It brings us to this value. So that I take one there. So that the scale should be maximum 1. All right. So it gives us a better shape that looks more or less in this particular pattern that we have up there. Is that clear enough?
Yes, sir.
All right. So
But the other formula, the other one you told us to do, the curve doesn't look like this.
the curve of which
Yes.
one?
The one we did, that
No,
is
it must not really curve like this. You see that this one is really actually curving, but this one is not curving, right? These things are just correlations that people have worked on, and they have brought out those formulas. It may work for some particular reservoirs, and it may not work for some particular reservoirs. For some reservoirs, it could be a good match, but for other reservoirs, it will not be a good match. That's why they just call it correlations. So
okay.
it must not give us this kind of perfect shape where you have, like this one is actually giving us a very good shape, but this
Yeah.
one is, the shape is not like, it's not, you see how this, if I look at the real one, you see how it's actually going, right?
Yes.
You see the behavior, but that one is just a straight line. So they are just correlations that I use in case there is no core data. But if there is a core data, then there is no need for you to use correlations.
Okay.
Oh, yeah.
All right.
So, but if there's no core data, you don't have a choice. You have to use that. So when we go now to the nodal analysis, did you look at it? Did you follow the video? I don't know
Only
if
the
you are.
first video. I was only able to follow the first video. You know, there are two
Okay.
videos. So I
Yeah, yeah,
watched,
there are two videos.
yes. So the first one, I
So
think
do
this
you
is
have, yes, this is the one. Do you have any worry with what you watched for this first one?
I have some questions, but I think I'll ask questions as we go through
No,
it.
If you have any difficulties, preferably we answer it before we continue.
Okay, I don't really understand the skin. Yeah, I'll say that skin part.
Okay. Now, if you look at this is the general pressure profile in a reservoir. This is our borehole that has been drilled. This is a reservoir where the hydrocarbon is moving into the borehole. Now, this may be a boundary. This may be a boundary where the reservoir ends. Now, this is the pattern of the pressure. This is the pressure profile along that particular reservoir. That means as you're moving from the reservoir, the pressure may be at this level. As you're moving gradually towards the wellbore, the pressure is dropping. There's some kind of a pressure loss along the line. So this is the normal pattern that you follow until the fluid now actually gets into the wellbore, right? But
Okay.
they may realize that at one point in time, it may follow this particular pressure profile, then it reach at some point in time, it doesn't follow the normal trend that it was supposed to follow. It either drastically increased or it drastically reduces
Okay.
away from the normal trend. That tells us that something is happening around this particular zone that is closer to the well ball. It means that this particular zone has been damaged.
Okay.
The value that characterizes that damage is what we call the skin factor. Skin is not this region. We cannot call this region a skin, but skin is just a dimensional term that is used to characterize a damage. So if they are telling you that we have maybe a positive skin, it means that a damage has occurred. If it is a negative skin, it means that no damage instead has occurred. It means that some kind of a stimulation. Most of this improved one happens after the well has been stimulated. That means they realize that the well is not producing as it has to produce. They now do some kind of activities which we are going to see later on, because we have to do hydraulic fracturing to explain how this improvement takes place. After the improvement, this is how the trend will be like. So there is an increase in permeability, but generally this is where the problem is. There is a drop in the pressure profile. That means more energy is lost within that particular zone. And that becomes a problem because the amount of hydrocarbon that they expect to enter the reservoir does not enter the reservoir. So it means that this particular zone has been damaged. So they have to always characterize that particular zone so that they can see how to treat the zone.
Okay.
It's clear enough, right?
Yes.
All right. So the main thing I want us to pick from this slide is that the main thing I want us to pick from here is that the production system in general, from the reservoir right to the separator. A separator is where the hydrocarbon comes to the surface and is separated between water, oil, and gas. When it gets to the surface, it enters an instrument which is called a separator. The separator now separates it into the different components, even though it cannot 100% separate it. But the production system from the reservoir right up to that separator is subdivided into different components. Each of these components can be characterized based on their different properties, right?
Yeah.
So when it comes now to the petroleum industry, this system may be one, the reservoir. The fluid move from the reservoir into the borehole that has been drilled. So from there now, it is a different component, which we call the piping system. That means the fluid has to move from the bottom of the borehole right to the top of the borehole. Of course, it passes through the casing and through the tubing and all of that. So all of that downhole system is what is another system. When it now gets now to the surface, it has to pass through the flow line, because we have series of pipes at the surface that it has to flow through it to the separator. That one is another component. Then lastly, now it gets now into the separator. That's another component. So different groups of petroleum engineers may be interested in analyzing different components. A reservoir and production engineer will be interested in analyzing this component, what is happening between the reservoir and the borehole, because immediately the fluid reaches the surface, their own job is done. They are not interested in what happens after the surface. Surface engineers now will be interested in what is happening now in this particular area. So the point of interaction between these various systems, with various components, is what we call a node. So for you to know how this entire subsystem is functioning, it is sufficient enough for you to analyze the functioning of the node. Once you know the functioning of the node, then that system, you can know how that system is functioning. The idea here is that the flow rate into the node should be equal to the flow rate out of the node. If there is no point where the flow rate into the node is equal to the flow rate out of the node, then it means that that function is not functioning. The system has died down, because there must be a point of interaction between component one and component two. If there is no point of interaction between component one and component two, it means that the energy of that system has died down. In that case, the company now will now bring in other method of energizing the system, maybe bringing artificial lift system by maybe pumping gas into the borehole. The gas goes and reduces the gravity weight of the fluid. It reduces the weight of the fluid. As a result of that, it can easily flow upward by buoyancy. Fluid can easily flow upward by buoyancy. We also have other things like the electrical submersible pump, where it re-energizes the system. So basically, we have sucker rod pump, electrical submersible pump, and when we have the gas lifts. Those are the three main types of methods that are used to re-energize the system. But they cannot do that if they have not done nodal analysis. Because if nodal analysis says the system is functioning well, then there is no problem. So if we come now, all right, so this is exactly what I'm talking about. If you draw a graph of pressure against flow rate, if you don't have this point of interaction, it means that that system is not functioning. You have to look for means to energize the system. So the process of generating this curve to know the performance of that system is what we call nodal analysis. All right, so this curve, this reservoir component, because we have said we are interested in this downward system, this reservoir component generates a curve that is called the inflow performance relation. And then this wellbore component generates a curve that is called the tubing performance relation, or the vertical lift performance. So that is the key idea around here that we are talking about. That's the key idea here. So this is a typical shape. I'm just going across because I know you have watched the video. This is a typical shape of the IPR, the performance of the reservoir. This is a typical shape of the performance of the reservoir. Then if you want to follow all of this, you can. All right. So when it goes now to the performance of the well ball, there are three things that comes into it. What happens if the fluid have to move from this well ball to the surface? What are the various changes that has to take place? There has to be energy that is lost due to what? Friction. The fluid has to overcome its own weight. And then if the pipe, this piping system, if the size of this pipe changes along the line, it means that the velocity of that fluid also will change along the line, because the velocity depends largely on the shape of the pipe. So if the shape of the pipe changes along the line, the velocity will change. Therefore, the kinetic component will now come in. There will be some extra drop in energy due to the fact that the velocity has changed. So we have three different components, but here we'll just deal only with two. We'll just deal only with two components. Here we'll just talk only about the friction component. We talk about the friction component. This is the friction component. Energy loss due to friction, and energy loss due to the hydrostatic force, due to that buoyancy force that it has to overcome. This one is the wellhead pressure. This is the wellhead pressure. Remember that if we are talking about the reservoir system, we are considering the reservoir pressure and the bottom hole pressure. We know that for the fluid to move from the reservoir to the bottom hole, it must have dropped a little bit. The pressure must have dropped. So the bottom hole pressure plus the amount of pressure that is dropped should be equal to the reservoir pressure, because generally the reservoir pressure should be greater than the bottom hole pressure. Otherwise, fluid will not flow in that direction, because fluid flows from a higher pressure to a lower pressure. That's the reason why, if I look at this formula for the reservoir system, you realize that the bottom hole flowing pressure is the same as the reservoir pressure minus that change, that loss in pressure in transit, that loss in pressure. Because if I take this plus this, it has to give me the reservoir pressure. You remember that in basic mathematics, if this one crosses on this side, it becomes what? Positive. But if this fluid has to move from the bottom hole, if I'm looking at the outflow component, that means the wellbore component, if the fluid has to move from the borehole to the surface, it means that the borehole pressure must be greater than the wellhead pressure. Otherwise, the fluid will not flow vertically upward. So the fluid flows vertically upward because it is moving towards a direction of lower pressure. So the bottom hole pressure in this case is equal to the wellhead pressure plus the pressure that is lost in transit. That pressure loss is due to the hydrostatic weight and is also due to the frictional forces. All right. So that's the key thing about this. So I'll go now to the second PowerPoint. How do we now generate these two curves? That's where our discussion for today is going to lie. How do we now generate the inflow performance relation? That's the first thing that we are going to look at. If we have to generate the inflow performance relation, for inflow performance relation, we are interested in the reservoir component. Remember that there is a particular pressure which we call bubble point pressure. The bubble point pressure is a pressure of the reservoir above which no gas is going to exist in a system. That means if I have a bubble point pressure of 2000 psi, if the reservoir is at 2,100 psi, it means that there is no gas in that system. So the bubble point pressure is separating the reservoir into a zone where the gas exists and a zone where there is no gas. Above that bubble point pressure, there is gas. There is no gas. In that particular case, we say the reservoir, they usually use the name, the reservoir is undersaturated. But below the bubble point, that is when gas bubbles start coming out. So generating the performance of this reservoir, in other words, the IPR, is going to depend on if the reservoir is above the bubble point or the reservoir is below the bubble point. So if I look at this, I have divided this is our bubble point here. If you look at the shape of the inflow performance above the bubble point, you realize that it is just simply a straight line. It's simply a straight line. But if you look at the shape below the bubble point, you realize that it starts by going in a straight line pattern, then it curves along the line. So we have to generate this curve using two different equations. Above the bubble point, we can just use a productivity index to generate this particular trend. And below the bubble point, we use what we call the Vogels equation. Now, what is a productivity index? Productivity index is just simply clear. It is the flow rate divided by the change in pressure. That's productivity index. The flow rate divided by change in pressure. So once I have flow rate divided by change in pressure, I can use this formula to make PWF is the bottom hole flowing pressure, the subject of that formula. Remember that our interest here is to draw a graph of pressure against flow rate in order to analyze the performance of the system. So I need these two components. These two components are these are the unknown in that equation. Because you know the reservoir pressure and probably you know the productivity index. So if I want to make this PWF the subject, this is what I have. So if I draw a graph of PWF against cure 0, it's going to give me a straight line. And the gradient of that straight line will give me -1 all over J. And J is our productivity index. So that's a simple equation that you have to use. That means for me to generate this particular curve, what I need is just the productivity index. I need a productivity index and I need a reservoir pressure. I will just go to Excel now and do a little bit of demonstration. Let's just assume that our productivity index J is equal to, let's say, 0.2, is equal to 0.2. Our reservoir pressure P is, let's say, 3000 psi, 3000 psi, and then the reservoir is above the bubble point. So let me see how I can generate that plot. I will have a graph. I will have values of P against values of cure, values of P against values of cure. All right. Now, we start from the reservoir pressure because the reservoir pressure is the highest pressure in the system. The reservoir pressure is 3000 psi. Now, I have to calculate flow rate. Oh, let me just say 3000 psi. Let me start reducing it. It now goes to 2500 psi because I want to have values of P, different values of P. So I'll just drag it down. I already explained this concept yesterday. I'll drag it down and leave it at that level. Now, if I go now to the formula, we're already through with this first one. Let's take it out so that it doesn't disturb us. All right. So now I know values of, let me say, these values are values of P, capital P, WF. These are values of PWF, not values of P. Reservoir pressure is constant. It is the bottom hole pressure that is changing. So we have to start with a bottom hole pressure that is equal to the reservoir pressure. If the bottom hole pressure is equal to reservoir pressure, of course, there is a static condition that is created. No fluid can flow because fluid will only flow if there is a pressure gradient. So if I want to make cure the subject in this equation, you realize that cure, if all of these components cross, cure is equal to J into reservoir pressure minus bottom hole pressure. So I go to that formula. I will now put equal to, I want to calculate cure. Cure is J, which is 0.2, into reservoir pressure, which is 3000, minus, that reservoir pressure is constant, minus the bottom hole flowing pressure. That's the bottom hole flowing pressure there. I'm going to click there because I want to drag it down so that it will calculate these other values. It will use this same formula to calculate these other values. That means in this cell, it will be using but 2500. In this cell, it will be using but 2000. So I click enter. There's a problem with formula. All right, let's redo it. We are equal to 0.2 times a star, so I'll put times in bracket reservoir pressure, which is 3000, minus the bottom hole flowing pressure, which is that. Then I close it and I take enter. It gives me 0, which is logical, because if the bottom hole flowing pressure is the same as reservoir pressure, there is no way fluid will flow. Fluid can only flow because there is a lower pressure in the bottom hole that creates that pressure gradient. So if our reservoir pressure is 3000 and the bottom hole pressure is 3000, then our flow rate is 0. So I will drag it down and it does the calculation for me. I will go and do the same thing as we did yesterday. Insert. I will take plot. I will take this. It has already plotted even. Let me see. I don't want it to plot. I want us, so don't highlight anything there. It plotted because we highlighted this. So let's see what will happen. All right, it comes out empty, and then we select our data. I prefer it that way. Select data, we add, then we can come to the x-axis. We have flow rate on the x-axis. We have flow rate on the x-axis. Then y-axis, we have the bottom hole fluid pressure. The bottom hole fluid pressure. So we take OK. So that gives us our simple IPR for above the bubble point. It gives us our simple IPR. You can go and add your axis, add your this. You can even add the title there. You can add the title there. There is no issue with that. But that's not our concern here. I just wanted to illustrate how you can develop the IPR using the productivity index. So if we go back here now, all right. So this is just an example of a situation. What if you have been asked to calculate the productivity index? They have not given you the flow rate. They have given all of this. This formula can easily be used to calculate. This is the formula from Darcy's law. Darcy's law of radial flow. That is because there are about maybe two types of flow. We may have linear flow and radial flow. We have linear flow and radial flow. Most of the time in our reservoir, the reservoir is mostly radial flow. That means the fluid is flowing in all directions around the well. Every position around the well at the margin of the circumference of the well, fluid is entering in all directions. That's the meaning of radial flow. So you can use this equation from there. You can make productivity index the subject. If you don't know productivity index, this is the formula of productivity index. So when I use this to calculate my productivity index, if all of these parameters have been given, then I can now go ahead to produce the IPR. Now, the next thing, our interest here is the Vogels equation because that's the most widely used. Saturated reservoir is just a reservoir at the point of maximum gas saturation. Above that point, there is no gas again. So we are talking about the bubble point. So a reservoir at bubble point is called a saturated reservoir. So in that case, the simple IPR cannot go again. We cannot use the productivity index to generate the IPR. We use what we call the Vogels equation. We use the Vogels equation to bring out the IPR, So if we have the Vogel equation, we can easily develop our IPR because we know that in this case, we are dealing with reservoir below the bubble point. So it is no longer a straight line. It may start as a straight line, but along the line, it will not give us a straight line. So this is a Vogel equation. And from this equation, we have three unknown. Remember that we are not interested in cure zero and PWF because that is the unknown of the graph. Those are the scales of the graph. If you have from your basic mathematics, you realize that the simple equation of a line is maybe y equal mx plus c. You don't need to know y and x because y and x denote the y-axis and the x-axis. What you need to know there is m and c. So we don't need to know cure and PWF. So the only unknown here is PR, which is pressure of the reservoir. The bottom hole flowing pressure, we don't need to know it. So the two unknown here are PR and cure max. PR is what will always be given. They'll always give you PR. So what we need to do now is to calculate our cure max. This is a simple formula to calculate our cure max. And we repeat again, if the productivity index has not been given, we can use this formula to calculate our productivity index. Now, if we go to the next example, this is a good example. They have given us calculate the flow rate when the bottom hole flowing pressure is 3000 psi, given the following data. So we have a bottom hole flowing pressure of 3000 psi. So we expect that the reservoir pressure should be greater than the bottom hole pressure. So this is our reservoir pressure, which is at 5651 psi. We have our bubble point pressure, which is the same as the reservoir pressure. So it means that we are now moving into a region where gas will start flowing, into a region where gas will start flowing. So the simple thing that I've asked here is to calculate the flow rate. To calculate the flow rate, we need the bottom hole flowing pressure, which has been given. We need the reservoir pressure, which is it that we have here. So what we need is the cure max. Cure max is the only thing that we don't have. But if I come here, I'll realize that cure max is the productivity index times the reservoir pressure. Reservoir pressure can also be denoted as P bar, so don't mind the different symbol. The different symbol. So if I calculate my productivity index, I can use this equation to calculate my cure max. So that's the productivity index that has been well calculated there. So it's giving us 0.192 stock tank barrel per day per PSI. Stock tank barrel per day per PSI. All right. So if I know my productivity index, I can put it in this formula to calculate my cure max. So this is the value of my cure max. I can now put that cure max now into this equation to calculate my flow rate. To calculate my flow rate. Now, that one is not really an issue. Our main issue is how to develop the IPR. Our main issue here is how to develop the IPR. So let's look at this second example and see how we can develop the IPR. So we now see the second example, say a well producing from a reservoir when an average pressure of 2000, from an average reservoir with an average pressure of 2000 psi, that's the reservoir pressure. If the flow rate is this, at the bottom hole flowing pressure of this, the bubble point pressure is that. Using the Vosges equation, calculate the flow rate. Oh, it's the same thing. It's the same kind of problem. All right. Now, even though we have not been asked to generate the IPR in this case, but let's see how we can generate the IPR. You have done your calculation. You have calculated cure max. From that cure max, we know that if this is my equation, this is my equation here. If I cross multiply, cure max will come in front here. So it's going to be cure max times all of these components. So let's go now to Excel and see how we can generate. I'll open a new sheet. I will have my PWF. PWF will start it from the reservoir pressure. We'll start it from the reservoir pressure. So what is the reservoir pressure? The reservoir pressure here is 5,651. So we will start that value from 5,661. Please, someone's mic is disturbing. Okay, all right. All right, so we start from there. Then we'll go to, let's say 5,000. We can just take 5,000. Then we can just take 5. We take 4,500. Then let's just highlight these two so that it follows a pattern right to 0. Anyway, there's no problem. Take 1,000. We have 500. Oh, not 5,000. Then we have 0. So this is our PWF. We need cure because we have to draw a graph of that. Now, if you come back to this, I said we have to make cure the subject. Cure the subject is simply obtained by sending cure marks in this direction. By sending cure marks in this direction. So if I have to send cure marks to this direction, my cure marks is 618.7.47. 618, so I'll put equal to 618.47 into, I open the bracket, 1 minus 0.2 into PWF all over P reservoir. All right. 1 minus, we'll open a bracket there. No, not yet. We have our 0.2 first. 0.2 first. We open the bracket now. PWF, that's the value of PWF, divided by P reservoir, which is constant, 5,661. 61. We
So
close that bracket.
that's the first value is 5651, not 5661.
Okay. No, there's still no problem. Let's continue. You can correct the value now. It's just an illustration, right? You can correct the value when you're doing it. Minus 0.8 into reservoir pressure, which is P dot, divided by, no, PWF is PWF. PWF divided by PR. So divided by our PR is constant, 56. Oh, what did I write there? Oh, 5661. Anyway, let's just use it like that. I don't want us to waste time. And then I close it. All that raised to the power 2. Remember, I showed all of this yesterday, how to put this power. But remember that at the beginning of all of this, I open a bracket in front, behind this 0.2. So if I don't close that bracket, Excel will not recognize that equation. Remember that anywhere you close a bracket, no matter how many times you open, you put brackets in the middle, make sure you close that first bracket. So I will click enter. They are still telling me that there's an issue with the formula. Oh, okay. Yeah, we are supposed to put times before that bracket. So we put star there. We are supposed to put times before that bracket. So, oh, still an issue. Excel is very complicated. So let's take it down and see if you calculate. All right. So it has calculated. Write down. Okay. So if the last flow rate does not give us that maximum flow rate, it means that there's a problem with your formula. There's a problem with your formula. Remember that if the bottom hole flowing pressure is 0, if I come to this formula, 0 divided by anything on this planet is 0. 0 divided by anything on this planet is 0. So all of this component disappears. So we have cure 0 all over cure max is equal to 1, which means that cure 0 is equal to cure max. So if your last flow rate is not the same as the maximum flow rate, then there is an issue. Then Nodal, go and check the formula. So I will now take this curve again. I will select my data. I will add. So yeah, I will take, that's the x-axis. We have flow rate on the x-axis. We have flow rate on the x-axis. Then on the y-axis, we have our bottom hole flowing pressure. Our bottom hole flowing pressure. All right, so that gives us our IPR. You can go now and add. You can go now where we have yesterday and add axis title for X and for Y. For X and for Y. So yeah, we can just call it our IPR. We can just call this curve IPR. And then down here, we have the flow rate. Flow rate. Here. Flow rate is in stock tank barrel per day. So if you like, you can put the SI unit, capital STB, stock tank barrel slash day. Stock tank barrel per day. Stock tank is an equipment that is used at the surface to store oil. It has its particular size. That's why they are using that particular symbol. So here we have PWF, bottom hole flowing pressure. So that gives us our IPR. So that's our IPR. You can also put a unit there. So that's our IPR for that particular reservoir. For that particular reservoir. Remember that all of this comes with a lot of uncertainty, because for you to calculate productivity index, you have used the formation volume factor, you have used the permeability, you have used the thickness, and most of these are measured through other means. Permeability can be estimated from well logs, thickness also can be estimated from well logs. So all of these things come with a lot of uncertainty. So for us to come back to it by using J, and that J was obtained. So can you hear me? Is my voice okay?
Yes, yeah, okay.
All right. So generally in a company, they don't use this productivity index to generate the IPR. They don't use this productivity index. What they are going to do to generate the IPR is to do what we call test point. They will take a particular bottom hole flowing pressure, and then they measure the flow rate at that particular bottom hole flowing pressure. Then they use that value now to generate the IPR. That is the most accurate way. So if you want to develop this IPR in a software like Prosper, if you don't give the value of the test point, that means a particular bottom hole flowing pressure and a flow rate, it will not be able to generate this IPR. All right. So if we want to construct this IPR, it depends now if our test point pressure is above the bubble point pressure, or it is below the bubble point pressure. Now, if it is above the bubble point pressure, the first thing is for us to calculate the J value of that particular test value that we have. Remember, the test value will give us cure and PWF. The test value is a single value of PWF and cure that have been tested, so they know that particular value. Reservoir pressure is constant, so they can use that particular value now to obtain the productivity index. They use that value of productivity index. Remember, if I make cure the subject here, all of this will cross. So it will be J into PR minus PWF. That's the same formula that they have used here. But here now, they want to calculate the flow rate at the bubble point. So that's why the pressure here now is the bubble point pressure, and they are using that value of J to calculate the flow rate at the bubble point. So in that particular case now, the value of J, this is the value of J that we have now, becomes a constant value that you have to use because it has been tested. It's not something that has been obtained from other parameters that comes in with uncertainty. So it has been well tested. So I can use that particular value of J to calculate my cure max. Remember that all of this is our cure max. So the equation is the same like in the first equation, but they have added the flow rate at the bubble point there, the flow rate at the bubble point there. So we are going to use this formula to see how we can generate the IPR. Okay, if the test is below the bubble point, this is a very complicated formula that you have to use to calculate the value of J. Remember, we know the flow rate at that bubble point, at that test point. We know the flow rate at the test point. We know the bottom hole flowing pressure at that test point, because these are the two parameters that we obtain from that test point. The value of the bottom of the bubble point pressure also is known, and I think the reservoir pressure is known. So we can calculate J from there. J will give us a single value. We use that single value also to calculate the flow rate at the bubble point, and then it gives us the same equation. So the only difference between the two of them is how to calculate J. That's the main difference between the two situations. Remember, I have said this is obtained in the company because they don't use the general formula of productivity index. They have to carry out a test so that they know a particular flow rate for a particular bottom hole flowing pressure. So we are going to take this example and see how we can generate that. A well is producing from a reservoir with an average P of 4,000, average reservoir pressure of 4,000 psi. If the flow rate is 2,000 stock tank barrel per day, So this is our test point that has been given. This is our test point that has been given. And the bottom hole flowing pressure is what? 3,000 psi. 3,000 psi. So this is our test point. This is our reservoir pressure, 4,000 psi. This is our bottom hole flowing pressure. So this is our test point. Remember, our test point is flow rate and bottom hole flowing pressure. Don't go and confuse between bottom hole flowing pressure and reservoir pressure. The bubble point pressure is 2,000 psi. So it already tells us that our test point bottom hole flowing pressure of 3,000 psi is above the bubble point. So it means that in that case, this is the formula that we have to use. And they are now asking us now to generate the Vogel, using the Vogel equation, generate the IPR. So my first task here will be to calculate J. J is flow rate all over reservoir pressure minus PWF. So I will just go to my Excel. I'll open another sheet. So I'll just write it there, J. We have J there. And then I go to the next cell. I want to calculate it. It's equal to flow rate, which is the flow rate. What was it again? The flow rate is 2,000 psi, 2,000 divided by the one down. I have to put it in bracket because I am taking PR minus PWF. P reservoir is 4,000. PWF is 3,000. So you can even just subtract and put a value. There's no problem. So I don't even need to put that. 3,000 minus 2,000 is 1,000. It's 1,000. So we have a productivity index of 2. Let's be sure of what we have done. Our flow rate is 2,000. Down here we have 4,000 minus 3,000. All right, so we are okay with that. We are okay with that. So that's our productivity index of 2. Now, what is the flow rate at the bubble point? What's the flow rate at the bubble point? So I will just have cure. I'll use small cure. Let's use that. So we have cure B. Cure B. All right. That formula is, remember, I have to always put equal to. So we have equal to productivity index, which is 2, into reservoir pressure, which is 4,000, minus bubble point pressure, which is 2,000, Then we click the simple formula. Oh, so you see what is happening there. You have to always be cautious. Instead of put divided here, I've put by times. So you have to put divided by there. So you click enter. So that's our flow rate at the bubble point. Wait, was it? Oh, sorry. It was okay. It was multiplication. The system corrected it for us, so we have to put a star. It's 2 times that. All right, so that's our flow rate at the bubble point. That's our flow rate at the bubble point. Productivity index minus reservoir pressure minus the bubble point pressure. Remember, our bubble point pressure here is 2,000. All right. So to generate our IPR, remember, we have the bottom hole flowing pressure and the cure. That is what we need to generate the IPR. I said our bottom hole flowing pressure always starts from the reservoir pressure of 4,000. So if I go to my table, so it's 4,000. 4,000. The next one will be 3,500. Not 500. 3,500. All right. So I now drag it. 3,000. What's happening? All right, write down, and then the last one now 0. We have to always end at 0. So our cure now, let's go back to the formula and verify. Cure is cure B plus our cure max, we have not calculated this. All of this value is cure max. We have not calculated this value. Let's calculate it. We need our cure max. So we have cure max. Cure max is J, which is 2 times, is 2 times what again? 2 times bottom hole pressure, which is 2000, then divided by 1.8, divided by 1.8. So we do not put equal to. So the system does not recognize it as a formula. So you have to put your equal to 2 times 2000 divided by 1.8. So once you don't put equal to, the system does not recognize it as a formula. So here I have equal to, the first is cure B, which is 4000 plus cure max. So I will just use this value here for cure max. So I don't need to type it again. So I will just take that value into 1 minus 0.2. I open my bracket, is PWF over PR. This is our PWF divided by PR is 4000. I close it, minus 0.8 into PWF. That's a PWF there. Something is up, there's an issue there. All right, let's continue. So we have cure max equal to, so we have our cure B. Let's just select this value from here. It is still okay. Plus cure max, that's cure max, into 1 minus 0.2. We have to put our times here. Remember, we had an issue the other time because of that. No, behind the, we have to put our star there. 0.2 into PWF divided by reservoir pressure, which is 4000, minus 0.8 into PWF divided by reservoir pressure, which is 4000. Then I close it to the power 2 because it is squared to the power 2. Then I close the first bracket. This bracket that I open here, I have to close it. So we have, so they always propose that issue, the correction. Yes, I think it's okay there. We take yes, and it gives us 0. If it doesn't give you 0 there, there's a problem. Because I've explained several times, if bottom hole flowing pressure is the same as reservoir pressure, there is a static condition that is created. Fluid cannot flow because fluid can only flow when there is a pressure gradient. So I will drag it right down there. Oh, what's happening? It's giving us this 0, 0 everywhere. Excel is very, very complicated. Immediately you make a mistake, So let's take it back afresh, please. We have equal to 4,000, which is our flow rate at the bubble point, plus we take this, which has our cure max, times, we open the bracket, 1 minus 0.2 into PWF divided by P reservoir, which is 4,000. I close it, minus 0.8. I open my bracket, P reservoir divided by 4,000. I close it, to the power 2. Then I close now that bracket. Yes. Okay. There's an issue. What's happening here? Sort this out. Let's take it again one more time. So we have 4,000 plus, let me use this value and see, 2,202.222 times, I open my bracket, I have 1 minus bracket, no, 0.2 first, 0.2 times, maybe that's the problem, 0.2 times, I open bracket, this divided by 4,000, I close the bracket, minus 0.8 times, I open the bracket, PWF divided by 4,000, I close the bracket, raised to the power 2, then I close now that bracket. All right, it's okay. So I take it down. Voilà, it's okay. I was calculating that I would give 0. I forgot that there's cure B. There's cure B here. So once this cure B is there, there's no way it can give us 0. So our flow rate can never give us 0 because of this cure B there. So that was what confused me the first time. So it's absolutely okay. So the flow rate starts from 4,000. So we can now plot our graph again. Take this, we select our data, we add x-axis, we take our flow rate at the x-axis, then we take our bottom hole flowing pressure on the y-axis, then we plot that. So that's what we have. So it starts from a reservoir pressure of 4,000. So our flow rate in this case is not 0. If I go back to this, you realize that it starts from here because we have a flow rate of 0. We have a flow rate of 0. So in this particular case, it cannot give us a flow rate of 0. It is starting from the bubble point. It is starting from this reservoir pressure, and this reservoir pressure is above the bubble point. So we have a situation where it doesn't start from the beginning. It doesn't start from the beginning. So that's our IPR. That's our IPR. So what you are going to do now is you are going to do the second. You are going to draw. Okay, I've not done that. We are going to draw this one. I think our test point in this case is below. So they say another well from the same reservoir produced at a rate of this when the bottom hole flowing pressure is 1,200. So it's just the same information. If the bottom hole flowing pressure is 1,200, it means that our test point is below the bubble point. Our test point is below the bubble point. Our test point is below the bubble point. And if our test point is below the bubble point, then we have to use now this particular formula. All right. So we are going to lay our interest more on the IPR for an oil well. This is the equation that is used is no longer the Vogel equation for the gas well. In the gas well, we use the Felkovich equation. We are not going to dangle into that for now. All right. So what I want to do now is just to roughly talk about the performance, because we have, remember from the beginning, we have talked about analyzing the performance of the well. To analyze the performance of the well, you need to draw the IPR, and then you need to draw the vertical lift performance. Trust me, there is no way we can draw this vertical lift performance with Excel. Let me not say there's no way. It's absolutely difficult, because there are some series of plots that you have to go through before you can actually develop that. So all of this is developed most at time using softwares, because it can easily be solved by numerical methods. Remember that from Darcy's law, I don't think we have the Darcy's law here. Anyway, let's look at this. From Darcy's law, you realize that flow rate depends on pressure. In pressure. So we'll see from this explanation, we will see why it is not easy for you to draw the IPR. All right. So the vertical lift performance, sorry, not IPR. So we are going to use Excel only to develop this IPR. We cannot use that to develop the vertical lift performance. So what is a vertical lift performance? The vertical lift performance is talking about the performance of the well ball. Remember, in the well ball, we have our well ball that has been drilled down to a particular point. Remember, this well ball has been cased. It has been cased down, right down there, to ensure stability. Then it has been perforated. This perforation enables reservoir fluids to move into the well ball. Then we also have our tubing. In that system. Then we may have packers here. The packers is blocking the fluid to pass only through the tubing, so that it doesn't go through the annulus, the space between the tubing and the casing, because it is blocked up here, it's blocked up there, and then the fluid is flowing. The fluid flows from there. So the fluid is moving from here right into the tubing, then to the surface. So if you have to understand the performance of this entire well ball, you need to understand how pressure drops due to friction between the fluid and this tubing, and even the casing, because it has to pass through part of the casing before it goes into the tubing. You have to understand how the weight of this particular fluid influence the performance of this particular system, because we have talked about three things that helps to reduce the pressure. We talk about friction, we talk about the weight of the fluid itself, then we now talk about the change in velocity. That change in velocity is called the kinetic head. Most of the time, we will ignore that, because that one can only come in if the size of the tube changes along the line. If the size of the tube is constant, then we'll assume that that particular component is constant and is zero. So it doesn't affect the performance of the system. So we talk about friction, and then we talk about the hydrostatic height. All right. So most of these, the PowerPoint is there, you're going to look at. So if you look at this formula, this is exactly what I'm talking about. This is a pressure gradient. This is a pressure gradient due to the hydrostatic height, assuming that we may have an incline, borehole or an inclined system. This is the pressure drop due to the kinetic. Remember, we are talking of dV. So there is a change in velocity. It's not just velocity, but a change in velocity. It's a change in velocity. That means if that change in velocity is not there, all of these components become zero. So we are now dealing with change in friction, and we are now dealing with change in hydrostatic pressure and all of that. Now, the change in friction is a complex formula that depends on what we call the friction factor. It depends on the friction factor, it depends on the density, it depends on the velocity. Remember, here we are not talking about change in velocity. We are talking about velocity as that. So it depends on the friction factor. So the most difficult part to estimate in this particular formula is the friction factor. The friction factor is given as this. And all of this depends on what we call the Reynolds number. It depends on the Reynolds number. So if you know the Reynolds number, you can easily know the friction factor. If you know the Reynolds number, you can easily determine the friction factor. So in this particular case, the Reynolds number or the friction factor depends on if it is a laminar flow or a tubular flow. If the Reynolds number is less than 2,100, then we are talking of a laminar flow. So we have this particular graph that was developed by Modi, From this graph, we can actually see the area of laminar flow, and we can see the area of turbulent flow. Then above this zone, they are talking of complete turbulence. So for you to know the friction factor, which is the y-axis, I need to know the Reynolds number. Then I need to know the pipe roughness also. I need to know the pipe roughness. So if I know the Reynolds number, I know the pipe roughness, I can easily determine the friction factor. So it's a whole lot of process. That's the reason why developing the tubing performance relation is very difficult. Now, there's another correlation. All of these are just correlations that people have developed to see if they can estimate the friction factor. But most of these things at times are not accurate. They are not accurate. So they say for a smooth pipe, we can use this equation. For a rough pipe, we can use this particular equation. Then for a turbulent flow, we can use this equation. So all of these are just correlations that we have. Remember, the PowerPoint is there. I'm just watching through it. So you have time, you go through it and see how you can enlighten yourself more and more. So this is just an example that they have given so that you should calculate the friction factor using the Collins-Brook equation. The Collins-Brook equation has been given there. This is the equation here. So you have to calculate the friction factor. So it's just an example that has been solved. You can go through it and look at it. So we want to just mention some few things about reservoir properties. We want to mention some few things about some reservoir properties so that when you start hearing them, you don't misunderstand them, or probably you don't get confused along the line. So let's take all of this off. So the most important aspect about reservoir properties is what we call formation volume factor. The formation volume factor. They have talked about soluble gas. What is gas solubility? This is the amount of gas that is in solution. Because if we said immediately the pressure of the reservoir goes below the bubble point, gas starts evolving into the reservoir. Not all of the gas will evolve out of the oil, because above the bubble point, all of the gas has gone into solution into the oil. That's why we talk of gas solubility. Immediately it comes out below the bubble point, what happens is part of the gas now starts evolving out of the oil. So in this particular case, we are talking about the amount of gas that is still left unevolved inside the oil. That's what we talk of solution gas. Solution gas is the gas that is still found inside the oil. This is the gas gravity. This is gas gravity. That's the formula of obtaining gas gravity. This is oil gravity. This oil gravity. And I think this is the formula also of obtaining the oil gravity if you know the density of the oil in API. API is American Petroleum Institute. That's an SI unit that is used to measure the gravity of oil. So if you know the gravity of oil, you can change it into the oil gravity. Now, when we talk of formation volume factor, the formation volume factor is measured in feet cube slash stock tank, not stock tank, or let's just say barrel, because it must not be stock tank barrel, because the oil must not reach the reservoir. Remember that as the oil is moving from the reservoir to the surface, gas is coming out of the oil. As a result of that, the oil is shrinking. The oil is shrinking. So this formation volume factor is measuring the shrinking ability of that oil. What is the volume of oil at the reservoir and what is the volume of oil at a particular condition? It may be at the surface or it may be close to the surface. You remember, you realize that that particular oil has shrink. It has shrink. So that's the meaning of formation volume factor. It's measuring the shrinking ability of oil. So these are things that you can just go through all of them. My interest here now is what is happening. This, what we discuss here, is just a simple way of obtaining the tubing performance relation using a single phase, assuming that it is a single phase that is flowing in our tubing. There is no way we can ever have a single phase in the tubing, because even if the fluid is leaving the reservoir as a single phase, along the line the pressure inside the tubing must be less than the bubble point, and immediately it is less than the bubble point, gas will start coming out from the system. You start seeing gas inside the tubing even though from the reservoir there was no gas. So the gas may be into the oil as a solution gas inside the reservoir, but immediately the pressure goes below the bubble point. That may happen inside the reservoir, that may happen inside the tubing. Immediately that happens, gas starts coming out of it. So we cannot talk of a single phase again. We now talk of what we call a multi-phase flow. So in this particular case, we talk of two-phase flow because we have gas and oil. So there are various types of flow. In the first case, remember, we talk of laminar flow and turbulent flow. That was all what we talked about. But here we are going to talk about different types of flow. We have the bubble flow. We have the bubble flow where we have just tiny bubbles that are coming out from the oil. Immediately you start going up, the pressure is dropping, more and more bubbles are evolving. Some of the bubbles start colliding with each other, producing large bubbles. In that particular case, we may be talking of a slug flow. And then as you go up, you realize that the bubbles become more larger and larger, more larger and larger. In that case, we may be talking of a churn flow. And it goes to a point where the thing now is now becoming more of gas. The entire tube now is occupied by gas, and oil is just flowing only at the corner, at this annulus between the gas bubble, because the gas has built up into a large gas bubble in such a way that oil is just flowing only at this annulus. Yeah, that's why we talk of annulus flow. So there are so many types of flow that comes in when we are talking of multi-phase. So it makes the thing become so complex. So from there now, this is our pressure gradient, which we have already talked about, and the friction factor. But in this case, we are not just talking about normal friction factor, but we are talking of two-phase friction factor, which becomes more and more complex. It's not like in the other case where we have a single-phase friction factor. Here we are talking of two-phase friction factor inside the tubing, so it becomes more and more complex. It becomes more and more complex. All right, so you read all of this, I don't think. So now, yeah, what I have just illustrated here is what is the effect of some different properties on the pressure inside the tubing, on the pressure inside the tubing. If this is our depth and this is our pressure, remember that as you're going up, you are now moving from lower depth to higher depth. What is the effect of all of that? You realize that the pressure, this may be the pressure profile when we have a particular gas-liquid ratio. Gas-liquid ratio, in other words, they'll call it gas-oil ratio, is the amount of gas divided by the amount of oil. If that value increase and increase, it means that more and more gas has been added into the system. Because if I have amount of gas divided by amount of oil, if the amount of gas, which is the numerator, keeps increasing, then the gas oil ratio will also be increasing. So if the gas oil ratio is increasing, the pressure profile does what? Drops. It keeps dropping. The pressure profile keeps dropping. Because at this level, it requires high amount of energy to remove the fluid from the bottom hole to the surface. But immediately the gas oil ratio increases, the liquid now in the tubing becomes more and more lighter. It becomes more and more lighter. So it is now easier for it to move from the bottom hole to the surface. So little energy will be lost in transit. All of this is explained in our day 2 of nodal analysis. You can look at this. So now, how can we develop our IPR? We can easily develop the IPR if we know the situation, if it is homogeneous. Homogeneous simply means that we have a situation where the amount of gas inside the tubing is so low in such a way that it doesn't affect the flow that much. In that particular case, we can use what we call the Pointman-Carpenter model or Pointman-Carpenter equation to develop the IPR. Why is this so complex? Look at this very well. We have our value of K. K is a function. Our flow rate depends on K, and K depends on flow rate. Remember the Darcy law I explained. The flow rate also depends on what? Change in pressure. So it's a circle. Everything depends on the other. Change in pressure depends on K. K depends on the flow rate, and flow rate depends on the change in pressure. So it becomes something that is so complex that you cannot solve it analytically. We can only solve it using numerical methods. You can always take your time out to look at the difference between analytical solution and numerical solution. I think if you did a subject like, we have a subject called further mathematics in high school. I think they have to do so many aspects of numerical methods in solving differential equations and all of that. All of those things are applied here. Even if you didn't do in high school, I'm sure if you are doing petroleum engineering, you must have done some of those concepts as basic preliminary courses in year 1 and year 2. If we have separated model where the amount of gas inside the tubing affects the flow that much, then we cannot use the Pointman-Carpenter model. We use the Hagedorn and Brown equation. This is the Hagedorn and Brown equation. These are not the only 2 models. We have more than 5, 6, 7 types of models that we have. I have just shown these 2 here to illustrate. I think there's somewhere I illustrate. Okay, so you can see different types of models that we have. We have the Dunes and Rose. We have the Franchise and Brown, the Hagedorn and Brown. We have Bex and Brill. So we have different types of model that you choose the model depending on your situation. It depends on you. And they have given some criteria here that you can use to choose some of those model, which one you want to use. I think as we are going along, when we get into Prosper, which is around week 6, we are going to see how we can model some of these equations using our Prosper software. So what I've explained here is we can easily use our Excel to develop our inflow performance relation, but it is difficult, not impossible, but it is difficult for us to use the Excel to develop the vertical lift performance. We are going to develop this vertical lift performance using our Excel. And when I get to that point, I will not explain what is inflow performance and vertical lift performance again. I will not explain those 2 concepts because I understand that we have already touched it here and it is well understood. So if you have any questions, you can ask your questions. Zero, if you have questions, you can also ask. Mercy, if you have a question also, you can ask. If not, then or probably you may go through it, and then if there's any issue, we can still answer later on.